Hello and welcome back to more functional analysis. I'm Fabian and together we are going to re-watch a video from the bright side of mathematics on open sets in metric spaces. I will give you comments, further insights and provide you additional examples to help you to improve your understanding of this abstract topic. Let's get started.
Please recall a pair consisting of a set X and a metric D is called a metric space. We've already discussed that if you fix a point X in a metric space, you can look at all the other points that have the same distance from this point X. Seeing that in the common geometry of the plane, this would be a circle around X. Or in a three-dimensional space, it would be a sphere, or you could call it a ball.
So we have already set the stage. Metric spaces are all about approximation of points. That's why we introduced the metric in the first place, to measure distances. What we are now going to do today is to focus more on neighborhoods of points that consists of all points that have a certain distance to the so-called center of this ball.
Now exactly this notion of a ball is what we want to generalize for an abstract metric space. We write b epsilon x and call it the open epsilon ball around X. It is defined as all the points y in our metric space X that fulfill that the distance from X to y is less than a given radius epsilon. However, this means that in the picture it's not the red line, it's everything inside. Now please note that for a given positive radius epsilon and a fixed point X from the metric space, this epsilon ball is never empty, because at least the point X lies in this set.
I would say this is a good way to warm up a little bit. Let's prove the statement that was made in the video, namely that given a metric space X D, a value epsilon greater than 0 and a point X from our metric space, that the corresponding epsilon ball b epsilon of X is not empty. Particularly, as what was said in the video, X is always contained in the epsilon ball. So, how do we prove this? Let's look at the definition of the epsilon ball again, here on the left. The epsilon ball with radius epsilon and center X contains all y of X such that the distance of X to y is smaller than epsilon. In our case, we want to check whether X is an element of the epsilon ball. Therefore, we need to calculate the distance between X and X, where we once plug in the center here and the point that we want to measure the distance to here. But both of these points are the same, and therefore the definiteness of the metric tells us that the distance is 0. In particular, the distance is smaller than epsilon, which shows that the above statement is correct. So far for every metric space. Let's take a look at an example of another metric space that is also easily formed. We want to take a look at discrete metric spaces. So we take X, which can be an arbitrary non-empty set, and we take D with a subscript D for discrete, the discrete metric. How was this metric defined? Recall. The discrete metric, so the discrete distance between 2 points X and Y of our non-empty set X, is either 0 if X equals Y. This is what we need to have a definiteness. And we say it's 1 if x is not equal to y. So now let's understand how an epsilon ball looks inside this metric space. So let's take an epsilon greater 0. And we want to understand what b epsilon of x is. Well, b epsilon of x by definition contains all y of x such that dxy is smaller than epsilon. So if y is an element of b epsilon x, then by definition the discrete metric for the pair xy is smaller than epsilon. So by definition. Alright, so what can happen now? We have a discrete metric, and as you can see from the definition, the discrete metric given a pair of 2 points can only take one of 2 values. Either it's 0 or it's 1. So namely, we need to check whether this inequality here can be fulfilled. So let's do a case distinction. So the case 1 that we want to look at is if epsilon is strictly smaller than 1. Then the above equation reads that the discrete metric for x and y, so this distance here, is strictly smaller than epsilon, which is strictly smaller than 1. So from the definition we know there are only 2 possible values, but if we additionally have that the discrete distance needs to be strictly smaller than 1, there's only one opportunity left, namely the first one up here. So in this case, the discrete distance between x and y needs to be 0. But by the definiteness of the metric, this dictates that x needs to be equal to y in this case. So what we have proven here now, if you look at where we started out, we took a point y from the epsilon ball with the additional assumption that epsilon is strictly smaller than 1, and we showed that x needs to be equal to y. So what we have shown here in the first case is that b epsilon of x is actually a subset of the singleton set. Recall from before that we also showed something that is true in every metric space, namely that the singleton set x is also contained in b epsilon of x. So what can we say now? The epsilon ball of x with respect to the discrete metric, if epsilon is strictly smaller than 1, equals the singleton set. So it's a little bit counterintuitive, but the epsilon ball is not a ball, it's just a singleton set. So as a quick exercise, you can do case 2, namely the case that epsilon is greater or equal than 1. Let me know your result and also the proof for it in the comments. And of course, as always, let me also know if you have questions. Let's take a look at another example of a metric space. Note that, or recall that functional analysis is also all about spaces of functions. So we want to take a look at a function space that we also know from other videos. We want to take the continuous function on the unit interval 0, 1. One metric So one notion of distance that we have for continuous functions is given via the metric d infinity. So, or the supremum or maximum metric in this case. This metric is defined for a pair of functions f and g to be the maximal distance of absolute values of the difference of f and g, evaluated at x, where x, of course, is an element from the closed unit interval. So how does a epsilon ball look like in this space? Let's find out. First of all, let's write down the definition again, but now with our precise setting. So let epsilon be greater than 0, and let's just assume we have a function f. Then the epsilon ball of f in our setting consists of all functions g from our metric space, which are continuous functions on the unit interval, such that the infinity metric of f and g is smaller than epsilon. Notice I just copied the definition and changed wherever I had additional information to the concrete information at hand. So this is not particularly helpful yet. Let's add further information, namely on this part here on the right hand side. So the infinity metric of f and g was defined as the maximum of f of x minus g of x absolute value. So this statement here tells us that for all x in the interval from 0 to 1, I have that f of x minus g of x absolute value is strictly smaller than epsilon. Let's take a look at a sketch that hopefully tells us what is going on here. All right, so this is our regular coordinate system. Just need the interval from 0 to 1 here. And let's say f is just a regular continuous function. So f is just a continuous function on the unit interval. So how does this function look like? Let's just say it starts out here and looks like that. Now the epsilon ball around f. A function lies in the epsilon ball if at each point in the unit interval from 0 to 1, I am not differing more than the value of epsilon. It is an absolute value. Therefore, I also cannot differ in the negative direction. And then I'm considering all points from 0 to 1, and I have to make sure that at no point distance between the function values, so I'm measuring a vertical distance here, is greater or equal than epsilon. I always have to be strictly smaller. So how can you imagine this? Well, think of a tube that has the same shape as our function f. So, and in 2D this works very well. So I have now an epsilon tube that surrounds my function f. And this epsilon tube makes sure, so that's the way it was designed, that no matter at which position I am, the distance will always be smaller than epsilon. So what is the epsilon ball now? Do we have it here in the sketch? Not directly, but we have some intuition what it means for a function g to be inside this epsilon ball. Of course, I cannot draw anything here because the space of continuous functions is infinite dimensional. This is just a two-dimensional picture. But the test I can offer you here is the following. A function g is inside the epsilon ball around f if its graph, so if I draw the function g, lies inside the epsilon tube around the graph of f. Then g will also be an element of the epsilon of f. On the other hand, if the graph of the function leaves the epsilon tube or merely just touches it, then the function is not an element of the epsilon ball. So let's also draw this case. So assume that the function h leaves the epsilon ball, then h will not be an element of the epsilon ball around f. Why? You can see it here at this position. Here, the distance between h and f will be greater than epsilon. Same happens here at this intersection. Here, the distance will be exactly epsilon, which is still bad if we want to lie inside the epsilon ball around f. All right. So the region between these green boundary lines, which are basically, as you saw in the construction, just translations, vertical translations of the function graph of f. So this region is sometimes called also an epsilon tube around f. And if you recall from your real analysis course, something like this also plays a very important role if we talk about uniform continuity of functions. All right, let's continue with the video.
Using this definition of an epsilon ball, we can now talk about a lot of important notions in a metric space. The first one I want to show you is about open sets. You may already know what open means in Rn, but now we define it for arbitrary subsets of our metric space X. So let's take this subset A, and I will use this symbol to denote a subset. Now descriptively, openness should mean that if you are inside a set A, you should never see the boundary of the set. In other words, if you fix an arbitrary point X of the set A, there should be enough points in all directions around this point that also belong to the set A. Of course, in order to describe this, we can use such an epsilon ball. We just have to choose a positive epsilon, but we can choose it as small as we need it. And if we can do that for each point separately, then we have an open set A. Therefore, the definition reads like a set is called open if for each point we can find such an epsilon ball. Of course, for each x you can choose another epsilon if needed. In the picture, this would mean if you get closer to the boundary, you need a smaller epsilon, of course. However, as long as you find for each point such an epsilon, we call the set open.
All right, now we have our first application of epsilon balls in terms of a new definition, openness of a set. So what I would like to do with you now is I want to study a set in our metric space X with the d-infinity metric and check whether this set is open. So namely, we want to take a look at the following set of continuous functions. We call the set A, just like in the definition, and we say that A consists of all continuous functions on the unit interval that are constant. So f is constant. So you all know what a constant function is. It is a function that only takes one value. And one way to express this is by saying that the function is of the form constant times the function 1 for a constant element of the real numbers. So 1 is just a function 1 of x equals 1 for all x in the unit interval. All right, we have a subset of continuous functions on the unit interval, and we have a term, openness. Let's try to find out whether A is open. Maybe before we start, let's check with our intuition and do the same sketch as before for a certain element of A. Note that in order to check for openness, we need to check a condition for each and every point. But to get a feel for whether this statement will be true or not, it makes sense as a preparation to start out with a single element and check for this specific element the openness condition. If it works, then we may have a chance to prove it also in a similar way for all other elements of the set. If it fails, then we already know the set won't be open. So which function should we start with? So clearly, the constant 1 function is an element of A. Yeah, it's just constant 1. I get it when I multiply this function with c equals to 1. How does the sketch look like in this case? It's a very simple one. So I have once again the unit interval. I have here the value 1. And the one function that I have here, well, it's just a horizontal line at the value 1. So now let's also take an epsilon greater than 0. How does the epsilon tube around the 1 function look like? This is also very simple. I'm just shifting the graph of this constant functions vertically by epsilon. So the distance I have here is epsilon, and the distance I have here is also epsilon. Let me move this a little bit. So the distance at each point to the green lines will be epsilon. Now recall the check that we had to find out whether an element is inside the epsilon ball around a function or not. We brought this back to talking about the graph of a function. So let me scroll up. If the graph of the function was lying completely inside the epsilon tube, then we knew that this function also would be inside the epsilon ball around f. Well, in this case, we want to know whether we find an epsilon tube such that within this epsilon tube only constant functions are. Why is that? So in the definition, we take an element outside the set that we want to check for openness. In our case, it's the function 1. And now we need to find a value of epsilon such that within this tube, so now I'm using the language of our metric space, there are only constant functions. This is the condition here below. Well, but why not just take a function that starts at 1 minus epsilon halves, and at epsilon halves hits this function here, and then just continues to be 1. Let's give this function also a name. Let's call this function g epsilon. Of course, we can also make this a little bit more explicit. So g epsilon of x should be the function that is 1 minus epsilon halves plus x if x is less or equal than epsilon halves, and it is 1 if x is greater than epsilon halves. Something that we immediately see here is, well, two things. The first observation, g epsilon is a continuous function. Of course, it's continuous. There are no jumps in here. Everything is fine. The other thing that you observe is g epsilon is not constant. So g epsilon is not an element of the constant functions. Why is that? A constant function just takes one value. That's why it's called constant. So inverting this definition, a function that is not constant takes at least two values, which we see here. So let me maybe add this here just to make sure. So g of 0 is not the same as g of 1. Therefore, the function is not constant. But, so our intuition tells us that g epsilon still should be inside the epsilon ball around the 1 function. And this is what we are going to calculate next. So let's calculate the infinity distance between our constant 1 function and g epsilon. So there's not much to calculate here. We can read it off our sketch, because if you look at this, the maximal distance between those two functions, which is what I'm interested in, is this part here. This is the maximal distance. So the distance is 1 minus epsilon halves, which gives me epsilon over 2. And this is strictly smaller than epsilon, of course. In conclusion, this tells me that g epsilon is an element of the epsilon ball around the constant 1 function. Now, taking everything together, also make this here white. Taking everything together, we have a function g, or g epsilon, that is not an element of A, but that is inside of the epsilon ball around an element of A. What we have shown here is the negation of the statement here. Let's look at this again. For each x in A, the negation of it would be there exists an x in A. Well, we just have the g epsilon for that. So there exists an open ball with b epsilon x in A. The negation of it would be for every epsilon ball around x, I do not have this inclusion. Epsilon was arbitrary, as you see here. So I showed that I find an element of A, namely the constant 1 function, such that no epsilon ball around 1, no matter how small the epsilon gets, is completely contained in A. So let's write this down here. So the b epsilon ball of 1 is not contained in A, therefore A is not open. All right. As a quick exercise, what you can do, let me know in the comments, is what are the open sets of the metric space with a discrete metric? Do you have an idea? Let me know in the comments. Now let's continue with the video.
Now, with your knowledge of open sets, you might also want to know what closed sets are. However, before we do that, let's talk about so-called boundary points. Let's take our arbitrary subset A again, and now we look in the picture maybe at points around here. At the moment, it's not important if the point we have chosen is an element of our set A or not. Of course, it's a point in our whole metric space X. The important thing is that with these points we describe something that we could call the boundary of A. And of course, we use the epsilon balls again for this. Now what you should see is, if we have an epsilon ball around this point, then we hit points that are in A, and we hit other points that are not. Of course, this clearly can happen.
Let me just briefly comment on this. As you may have already seen in this video, the sketch that we have here in the video is by no means a realistic example for every metric space that we have. It still makes sense to save this image into your brain. Why? It will help you to recall the definition if you are unsure about it. If you can make the sketch, I guarantee you that you will always come up with the correct definition. Let's take a look at the definition.
Definition reads: a point X from the whole metric space X is called a boundary point for A if all open balls around X contain points from A and the complement of A. For the formula here, we just use the intersection and say this one can't be empty, and also not the one when you use the complement of A.
So, a new definition comes up. We have an example already at a very developed stage. Let's check out if we can talk about the boundary points of A. So what are the boundary points of A? As you will see in the video, this will ask about this set. So del symbol of A. What is it? So the first thing that we see is this is something that we once again need to check for every point in a set. Yeah, and it is a boundary point if for every epsilon ball we have these two conditions fulfilled, namely that the intersection of an epsilon ball with a set and with its complement are both non-empty. So let's maybe start by checking whether the constant 1 function is a boundary point. Well, as we saw before, or here above in the calculations, the intersection of an epsilon ball around the constant 1 function with the set A is non-empty. So this is always the case. So why is that? Because 1 is an element of A, and 1 is also an element of the epsilon ball around 1. This is true in every metric space, and this is true by assumption. So this is the first condition. The second condition that we need to check is, what about the complement? So is also the intersection of the epsilon ball around 1 with the complement of A non-empty? So we know an element that is in the complement of A, namely the function g. G is not in A, so this implies g epsilon is an element of the complement of A. At the same time, g epsilon is an element of the epsilon ball around 1. So this actually is a superset. Oh, let's write it like this. This is a superset of the singleton that contains g epsilon. Therefore, it's also not empty. So let's go again back to our sketch here. Recall that we started out with one specific function inside A, the constant function 1. Would the construction been very different if we would have taken another constant function? So to say, if we took not 1 but c times 1? No, it wouldn't have been. Actually, this would just mean to shift everything that we did upwards or downwards depending on the value of c. It would still work out. Therefore, the argument that we carried out here would also work for every other element in A. So, similar proof shows indeed that c times the 1 function is in A for every c in R. So this allows us to conclude that actually A is a subset of its boundary. So this may seem counterintuitive, but only because you may still think of the image on the left-hand side. Clearly, on the left-hand side, the boundary is not a subset of A. Or like here, it's or a superset. Yeah. So this just tells us the intuition that we have for two-dimensional objects or sets does not apply always in the case of function spaces. So we really have to be careful about this. So we have one inclusion. What about the other inclusion? Is it true or is it not? Well, let's see. Let's take a function f from the boundary of A. This function can either be constant or it can't be constant. So let's assume f is not constant. So f is not an element of the set A, which is where we store all constant functions in our space. Not being constant means there exist 2 points A and B in the unit interval such that f of A is not equal to f of B. Yeah, if it's not constant, the function needs to take 2 different values. Let's say it takes one value at A, another one at B. So what can we do now with this function? Well, we now want to compare the distance to each and every element in our set A, because we want to use the property of being a boundary point. So let us take a C in R and calculate the infinity distance between f and c times the constant function here. So by definition, this is nothing else than the maximum of f of x minus c for all x in the unit interval. Yeah, so I really compare each and every point with the value c and calculate the distance. Now I can also pass to a smaller set if I allow the maximum to get smaller. So the maximum over all function values that I have here will be greater or equal than the maximum that I have if I only compare c to the value f of a and to the value f of b. And of course, because f of a is not equal to f of b, I get that this maximum, while it may be smaller than the maximum over all function values, is still greater than 0, strictly greater than 0. So now look at what I'm doing. Now I take this number here, from which I already know is greater than 0, and just say, you will be my epsilon. Then I see that that for all c in R, c times 1, so this function here, will not be an element of the epsilon half ball around f. Because epsilon halves is of course strictly smaller. It won't be an element of the epsilon ball. So I got confused because the unequal sign is in the other direction. So the distance of f to c times constant 1 function is greater or equal than epsilon. But in the epsilon ball, there are only elements that have a distance strictly smaller than epsilon. What can I conclude from this? Well, let's see. This tells me that the epsilon ball of f intersected with A is empty. Why can I intersect with A and still be empty? Well, I checked for every function in A. Note that we wrote down functions in this way. C times a constant 1 function. This gives me every constant function that I know. I can show for every constant function that it won't be an element of the epsilon ball around f. Therefore, the intersection with A will be empty. But this is a contradiction. It contradicts the fact that f was assumed to be constant. And f, of course, is in here. And f was also assumed to be in here. So it cannot be empty. It should contain f. But I now have this contradiction here, which means that this assumption here is actually false. So, via contradiction, I now showed that if f is an element of the boundary of A, or of the set of boundary points of A, then f needs also to be in A. Or, to sum it up, the boundary points of A are equal to A. All right. Let's jump back to the video.
To this set. Now you can remember, an open set is exactly such a set where all the boundary points are outside of A. When you see this, then you immediately understand what a closed set should be. It should be a set where all the boundary points belong to this set. Using the same formula, this reads A is closed if and only if A with the union of the boundary is A again.
So, in other words, we have shown that A is not open, A equals the boundary. So we can also show, or we can say now with the new terminology that we have, A is closed.
However, that's not what one uses as the definition for closed sets. The definition is much simpler. A subset A in X is now called closed if the complement in X, which is AC, is open. This makes sense because the boundary points of A and the complement are exactly the same, and this just means that all the boundary points belong to A and not AC. Now the last notion for today.
So before we come to the last notion, let me say again, so we showed A is closed by the above. We also know that A is not open, but as A is closed, we know that the complement of A will be open. Yeah, so don't confuse it because there's a lot of confusion going on. Not being open does not mean that one is closed. Being open is equivalent to the complement being closed. Yeah, be careful with this terminology. It can be confusing, and yeah, it takes a lot of caution not to fall into a trap here.
Will be the so-called closure. The name already tells you, if you start with an arbitrary subset A, what you want to get out is a closed subset. How to get this you might already know. You just add all the missing boundary points, so you form the union with the boundary. And this is what we call the closure of A. And we denote that with A overline.
Alright. What about the closure? So we also see the closure of A, in our case, equals A. This brings me also to the closure of this video. Thank you very much for watching. If you learned something new today, let me know via the like button. And if you have any questions, comments, or suggestions, let me know in the comment section. I'm already looking forward to it. Have a nice day and goodbye.